The following presentation is recovered from a 2021 PDF draft time capsule for Foundations of Differential Geometric Algebra by Michael Reed, who is me, the author of Grassmann.jl computational language. Welcome to Foundations of Differential Geometric Algebra. Differential geometric algebra is a style of computational language which I've been exploring for several years now. And in this presentation, I'd like to look at some of the mathematical foundations that are involved in this. The computational language which I've been designing for differential geometric algebra over several years is a highly abstract concept which I've been developing in my mind quietly and manifesting in computer programming language using the Julia language and the Wolfram language. When I set out to work on this, the tools I desired based on these foundations didn't exist. So I went ahead and created the kind of foundations I envisioned. Please help sponsor and fund this research and development project. While there are many tricks and special techniques I used specific to the programming languages I implemented this computational language for, this presentation is primarily based on fundamental mathematical principles. So it's going to try to avoid being specific with the programming language. The goal of this presentation are to emphasize some specific foundational aspects which I believe some people have overlooked in the past and thought were uninteresting. I've chosen a particular theme to go along with these foundations that we're studying here, and this theme is what I call differential geometric algebra. So that's what we're studying here. So why is geometric algebra fundamentally important? Well, from the perspective of geometric algebra, we have a unified foundation for the complex number flat geometry, the quaternions with a 3D rotational algebra, linear algebra and bilinear transformation, the exterior forms algebra, and the multilinear determinant, a quantum logic lattice, differential geometry, the conformal geometry and the projections, group representation, and also the combinatoric hypergraph. So we are dealing with the algebraic unification for geometry and mathematical physics. Alright, so that's a mouthful of words. But what is it that actually makes geometric algebra fundamentally important? Well, it provides the generalization to the right-hand rule for higher dimensional orientations. So what do all of these things have in common, really? Well, suppose we choose a two-dimensional submanifold, an area inside of a three-dimensional space, and we look at this space as having an orientation, and we want to have a complement to that space which also has a direction or orientation as well. We can generalize this concept to not just the cross product in three-dimensional space, but in arbitrary spaces, and there's an algebra for this, and this is geometric algebra. And all of these different concepts here, they involve a generalization of this that's utilized in some way. So the goal here is to combine the algebraic foundations of geometry with differential calculus, and to have a kind of universal computational language that serves as a common foundation for many different mathematical things. taking a look at this graphic from David Hesteny's paper about geometric algebra and calculus, we can see that geometric algebra has taken many years to be passed down through written material until it's reached its current stage at which David Hesteny was making this graphic. And now we've reached a new age where we're implementing in computational language these concepts of geometric algebra, and it's going to be able to be transmitted in a different way, to be used for research and for learning and education and teaching different things. However, along the way of this historical transmission of information, it wasn't entirely a planned out, coordinated transmission. So there have been some missing pieces of information that didn't get transmitted in all parts of, this network of transmission. And one particular aspect which has gotten lost in a lot of people is the original foundations of the Grassmann algebra before the Clifford algebra. And there's some aspects of that which are important and need to be taken into account. With my Grassmann.jl computational implementation of geometric algebra and the Julia language, which is implemented across several packages, including the DirectSum.jl package and the AbstractTensors.jl and Grassmann.jl, which is the Differential Geometric Algebra on the discrete manifold implementation. So that's some of my background with implementing specific programming language designs for differential geometric algebra, where I spent several years refining and experimenting and trying out different computational language designs. And over this time, I've learned some fundamental universal mathematical principles, which is what I'll try to be focusing on in this presentation. Now, since we've talked about the foundations of differential geometric algebra in terms of linear dependence with the exterior product and the geometric product constructions that we can create from that, we are now going to take a look at one of the heart of the matter of differential geometric algebra, which is the Grassmann's duality and the Hodge complement. And this is where we're going to take a look at some of the definitions and theorems that we're going to cover in this presentation. And I saw that there's a few people out there who somehow don't use exactly the correct definition or something that's incompatible with this. So I wanted to kind of make it clear what the original Grassmann and Hodge definitions were, or at least what they should be in terms of a modern differential geometric algebra foundation, and how they should be, what kind of theorems you can talk about and things like that. So I wanted to be kind of more specific about it. And that's why in this presentation we've built up the foundations and we've created a geometric product and so on. And we're now ready to talk about the original Grassmann's duality and the Hodge complement. So what are we actually talking about here? And so we'll define it. We're talking about the Grassmann-Hodge complement, which is often represented with the star. So let omega be some kind of exterior product, and then we let star omega be the reverse of omega times I. So then it turns out that this star operation takes something from an exterior graded space of P to an n minus P space. And this is called the Grassmann duality and the Hodge complement. So what we're doing here is we're combining several different concepts we've previously covered. We're combining the exterior product, and we're applying the reverse anti-automorphism, and then we're applying the geometric product with the pseudo-scalar in the space. There's this thing called the orthocomplementary propositional lattice in quantum logic, and for that you need something called a join, a meet, and a complement operation, which is analogous to a union, a intersection, and, well, a complement. And this is associated with something called the De Morgan's law. And what we have is we have these operations, which is the exterior product and the regressive product, which Grassmann originally talked about, and the complement operation, which talks about the duality. These satisfy the property that the complement of the regressive product is equal to the exterior product of the complements. And that is the De Morgan's law, which is analogous to the law that we have in logic and set theory. However, this is where we're going to have to nitpicking our statements about what we're talking about, because this is only completely true for Euclidean or flat algebras in general. So the original Grassmann complement must be used, which was before we introduced the metric tensor, which was the Hodge complement. So let's get more precise with our language. When we mean original Grassmann complement, we're talking about this kind of vertical bar notation that is associated with the original Grassmann writings. And in this operation, it's the same as the Hodge star complement, but it is always with the Euclidean flat metric where g equals to 1. And so when we have original Grassmann complement, that's when this De Morgan's law is satisfied. In general, though, we have, because of the geometric product, the introduction of a metric tensor value that's not necessarily equal to 1, depending on the tensor bundle choices that we make. And we can construct the interior contraction using the operation with the regressive product and the complement, the Hodge complement. It turns out that we actually need both of the Hodge complement and the original Grassmann complement in a hybrid fashion if we are to make kind of a really modern foundational construction of these terms. Because when Grassmann was originally talking about this, the theory wasn't as far as it is now, the understanding behind it and the algebraic language that we have, that we can use to talk about things. And because now we understand things better, I can say in retrospect that the interior contraction formulation that we're looking at here, which we're going to get into more in a bit later, but this is just kind of a preview of that, or a side note, that we need both the original Grassmann definition and the Hodge definition simultaneously in the foundational construction. And it's not just some kind of, random thing. It's actually both of them are needed, and these are the ones that are needed: the original Grassmann complement and the Hodge complement, and not some other arbitrary choice that you could be making. And by taking a look at some of the theorems and properties that this complement needs to satisfy for differential geometry, for example, we can understand that this is indeed the right choice that we need to make, that this is the Grassmann and the Hodge complement that's needed. And the reason why both of them are needed is because, as I said here, it's this De Morgan's law. It actually only applies with the flat metric when g equals to 1. Otherwise it doesn't apply, and that's why the definition of the regressive product that's used in the interior contraction is based on the original Grassmann complement operation in the construction of it. And so even though that's the case with the regressive product, it's still the case that the interior contraction uses the Hodge complement in combination with the regressive product that's based on the original Grassmann complement. And so this kind of nuance makes us kind of aware that there's both of these complements: the Hodge complement, which has a metric built into it, and the original Grassmann complement, that both play a fundamental role in the foundations of what we're talking about, or what we're going to talk about with the interior contraction coming up. And in fact, this is something that's fundamentally built into the computer language design that I've been working on. So it's just a part of the reality of working with differential geometric algebra, that there's a Hodge complement, which is the primary definition, and the original Grassmann complement, which is another primary definition that's kind of more specific than the Hodge complement. Alright, so we've talked a lot about the complements and how there's these two different complements and so on, but that's all a bit abstract because it's just in terms of algebraic expression that we took a look at it and the definition of it. But we could take another look at an example of it in terms of the hypergraph representation. If we view multivectors as hypergraphs, for example, if we have V1, 2, 3, a hyperedge, and we take the complement of that, that is another hyperedge. And when we visualize it in terms of the connectivity of the hyperedges, we can understand that the complement hyperedge truly takes up the rest of the total space that we have. So if there are 7 vertices, it makes a tetrahedron out of those other 4 vertices because of the ones that were taken up by the 1, 2, and 3 triangle there, that the complement of it has to be a tetrahedron. Now, it's not just the case that we have a complement here, but these have orientations. The triangle has an orientation, and the tetrahedron is a hyperedge that has an orientation, and the complement operation sometimes has a metric tensor that also weights the complement operation in a particular way. And so this is a bit more complicated than just hypergraphs, because it's has orientation and sometimes the weighting from the metric built into it. Let's take a look at one of the most important theorems or axioms in differential geometric algebra that are out there. So this isn't something that I came up with. This is something that's been discussed in the foundations of Grassmann algebra and differential geometry in various places. But this particular proof that I've constructed here, I haven't seen that before. This is a new way of thinking about this. So in some of the other literature, this is taken as an axiom. For example, an axiom for Grassmann algebra. But in my foundations here, I'm going to look at it differently. I'm going to look at it as a theorem that's derived from the definition of Grassmann and Hodge complement that I've given previously. Because in some of the other foundations, there wasn't such an explicit definition of the Grassmann-Hodge complement as explicit as the one that I have given here. And so as a result of that, because my definition is much more explicit, I can turn things around and I can make the complement of a complement theorem a thing. Instead of having it be an axiom, I can make it a theorem and look at it from that kind of foundational perspective. And so that's what we're doing here, and I don't think I've seen this particular kind of theorem approved before for this in this kind of way. So how does that work? Well, we'll let omega be a grade m element, and we take the complement of this, and that's supposed to be -1 to the m times n minus m times omega times the absolute value of I squared. This is a fundamental theorem that's foundational and important. And so it's important to be able to kind of prove this and to verify that the choice of Hodge complement that we've made actually satisfies this theorem. And it does. So we can take a look. So let omega be a grade m element, and then we can rewrite the expressions using the definition I gave previously. And then what we can do is we can take the reverse of omega and extract out the -1 to the m times m minus 1 over 2. And because we can extract that out, we have a different expression, and we can once again extract out another -1 raised to an algebraic power, and by extracting the reverse operation from the omega times the pseudoscalar. And by doing that, we can now rewrite the pseudoscalar as a square product, and we just have the omega by itself now in the product, and we have a product of -1 to some raised to some power. And this expression can be rearranged by using algebraic manipulation of these powers of -1. And if we write it in such a way that we have -1 times m to the n minus m, and -1 times n minus 1 over 2, then that is once again a reverse operation that can be replaced in the, or rewritten in the expression. And so when we rewrite this expression, what is it? Well, instead of I squared, we have the reverse of I times I, and we have this, and the reason we want this is because we can write this as the absolute value squared. And now we have the result. Actually, that is the result of the theorem, and the result follows because -1 to the n times n minus 1 over 2 times I squared is the reverse of I times I, or the inner product of I with itself, or the absolute value squared of the pseudoscalar. So the theorem is proved. And we just did it using the foundations of differential geometric algebra that I've presented here. And I don't think I've seen a proof of this theorem using these kind of foundations anywhere else out there in the literature. So I think this is an interesting new way of looking at it and being certain about the truth of this theorem, instead of talking about as an axiom and having the complement be some kind of mysterious operation. We've changed it around. In my foundational perspective, I have an exact, explicit definition of the Grassmann-Hodge complement, and the complement of a complement thing is a theorem instead of an axiom. So I think that's an interesting way of looking at it. Let's take a look at foundationally important properties of complements, since we've taken a look at the complement of a complement theorem in its general form. There's a more specific form restricted to just the original Grassmann complement. So when we just restrict ourselves to the Grassmann complement axiom with a flat manifold, let omega be a grade M element of Rn, then the complement of that has to be minus 1 raised to the m times n minus m times omega, since the absolute value of the pseudo-scalar squared equals 1. The following lemma and corollary are helpful. Let omega be a grade M element, then the regressive product of the pseudo-scalar I and omega equals omega. So the proof of this is fairly simple, actually. If you apply the Grassmann duality principle with the regressive product and the exterior product and rewrite the expression as an exterior product, then we can simplify the expression by observing that the Grassmann complement of the pseudoscalar is just 1, and then that means that we are taking the exterior product of 1 with the Grassmann complement of omega. And because we are now just saying that we want the inverse Grassmann complement of the Grassmann complement of omega, this just means we're just asking about omega. And so the result equals omega, and the lemma follows as a result. Now another obvious corollary is that the reverse of omega times the pseudoscalar equals the inner product of I times omega, since I times the inner product of I and omega equals the regressive product of I and star omega, or the Hodge complement of omega. And by the lemma that we just observed, we know that this is just equal to the Hodge complement of omega itself, and therefore it equals the reverse of omega times I, the pseudoscalar, and the corollary follows. So it's just kind of an interesting, obvious thing. Once you know all this thing about the Grassmann complement, the Hodge complement, and these theorems, these kind of things kind of just follow as an obvious result that kind of makes sense once you get into these type of results. Now let's take another look at an example of a theorem, which is the interior and exterior product with the Hodge element. And so if we let omega be a grade M element, then the regressive product of omega and the Hodge complement of omega all times the pseudoscalar I is equal to the exterior product of omega and the Hodge complement of omega. This is kind of a fundamental observation that's important and that you find maybe in some way or form in some places. And this is a expression of it in terms of the operations that we're using in the foundations of differential geometric algebra. And we're going to attempt to provide a proof of that here by expressing it in this way. So based on the properties and the expression rewriting that we've done, we can rewrite the expression in this way such that we end up with a exterior product expression instead of a regressive product. and then we can factor out the metric tensor component from the Hodge complement component in such a way that we can apply the complement of a complement axiom restricted to the original Grassmann complement to the expression, and rewrite the expression in such a way that we have -1 times m to the n minus m. And then we have the exterior product properties that we can apply and rewrite the expression once again, and we can have a simpler exterior product expression as that we can now refactor actually again the metric tensor component that we factored out into the exterior product expression that we have in order to make the Grassmann complement into a Hodge complement, because this extra factor is basically what is the difference between those. And then we just note that we have to multiply this whole expression by I, the pseudoscalar, in order to prove the theorem. And so that's how we can get theorems like this that we can observe using differential geometric algebra when we explore the properties of the elements and the algebraic expressions that we can make. So we've seen that we can construct expressions using the Grassmann and Hodge duality complement and the exterior product and the regressive product, and we can create expressions that are equivalent to each other and make proofs of that. Now, another thing that we can do is we can extend this proposition of writing variants of expressions by making variants of expressions that involve the interior product and the exterior product. So suppose now, what if we want to write the exterior product not just in terms of a regressive product, but an interior product? And this is what this theorem states, that you can do this, and you can also write an interior product in terms of a regressive product, which can be written in terms of an exterior product. And so this is kind of another variation on extending beyond what we just did in the previous theorem, which goes to show that we can find interesting formulas relating expressions with exterior products, regressive products, interior products, and the Grassmann-Hodge complements. And if we move on to the next theorem, actually, here's another more simple result that we could consider, that if we have eta and omega being grade m elements, then if we take the reverse of those elements, the inner product still equals the other interior product. And that's due to the property of squaring the powers of -1, which just cancels out those, making the expressions equal to them. Having taken a look at some of the variants of expressions involving interior products, we can now take a look at this corollary involving the absolute value of an element omega squared, or the interior product of omega with itself. So if we take that and multiply it times the pseudoscalar, that equals an exterior product expression based on the theorems that we've been taking a look at. We can see that that's a result basically by applying the last few theorems. And then because we've now rewritten the interior product as the exterior product, and we can actually go a bit further and not just rewrite this as an exterior product, but we can make it a geometric product. and rewriting this as a geometric product, we have the Hodge complement still in our expression, but even that can be rewritten as a geometric product. So we rewrite the geometric product once more, and we obtain the reverse of omega times I, the pseudoscalar, and that turns out to be just the absolute value of omega squared times I. And this is basically if and only if we choose basically that the interior product of omega with itself equals the reverse of omega times omega using the geometric product. And this is basically one of the reasons why we have chosen some of the definitions we've chosen in terms of the original Grassmann algebra foundation. Is we want to have this arrive at this corollary, which helps make sure that we're using the correct algebraic properties. It's now time to address a divide in the geometric algebra literature. Specifically, if you've done enough studying about geometric algebra and Grassmann algebra, you will know that there are both a left and a right contraction, which can define the variance of the interior product. Now, in this presentation, I've tried to avoid up until now addressing which one of these I've used, because I want to address it now at this point where we have enough foundations to talk about this. But up until now, I've just been using the right contraction, the original Grassmann right contraction as the default interior product for what we're talking about. And this is true to what the original Grassmann algebra did and what John Brown was talking about in his exposition about Grassmann algebra. What actually is the difference between the left and the right contraction? Well, if we take a look at the table we have here, this table which I created demonstrates that when we look at the geometric product construction of the left and the right contraction, where it's the reverse of eta times omega using the geometric product, and then using a grade projection using s minus r or r minus s to project onto the grade space. So what was the actual difference there between the left and the right contraction? It was s minus r and r minus s. And due to the way grade projection works, you can't have negative, grades. So the operation actually just is zero when it's negative. And so that is the difference between these two operations, is how the grade projection behaves based on the parameter s minus r or r minus s, which is determined by the grade of the input elements eta and omega, r and s. If we look at the other side of the expressions in the table, we see that we can use a regressive product in the Hodge complement to express the same contraction product instead of using a geometric product with a grade projection. So by just applying the grade projection on the inputs omega and eta, we can restrict ourselves to the S and R grade, and then we can use the regressive product in the Hodge complement in this compositional way, such that it gives us the same result as when we use the geometric product and the grade projection. But what is fundamentally important here, which differentiates some of these expressions, is the role of the reverse anti-automorphism in the expression. So in the geometric product expression, we use a reverse anti-automorphism, whereas in the regressive product expression, we don't require it. This is where I've discovered a multiverse of variants of interior products, which is a rift in the geometric algebra literature. And this table here maps out what I've discovered out in the wild world in the wild west of geometric algebra, where there are different types of expressions out there. And in particular, the way this table works is it's actually quite systematic, and it's fully kind of maps out most of what we would see in terms of variants of these. And the most important one really is just the Grassmann and the conventional variants. Now the Grassmann one is what we've been talking about in this presentation so far. It's just the first row in that table. And now what happens if we just focus on the right-hand side of the expressions? We see how the geometric product is a composition of two elements, eta and omega, and one of them can have an anti-automorphism applied to it, which is the reverse tilde operation, and the other one doesn't. And you can swap around which of the input arguments has the anti-automorphism applied to it, or it could be neither of them or both of them. Now the Grassmann original definition would involve a single anti-automorphism on the left hand argument, while the conventional approach has no anti-automorphism in the geometric product expression for the contraction. Instead of using the geometric product expression on the right hand side of the formula, we can also take a look at the regressive product expression and how the anti-automorphism is applied to the input arguments and how they compare across the table. And similarly, we can find that there's a pattern which is similar but not exactly the same pattern as with the geometric product expressions. Alright, so why would I bother tabulating this multiverse of possible expressions for the interior product contraction, which has a left and a right variant and a Grassmann variant and a conventional variant? Well, the reason why this is tabulated here is because as I was reading the geometric algebra literature and differential geometry literature and trying to unify these things in my mind and build a foundational structure that is consistent across all these different things, I realized that some of the literature was using the conventional definitions when referring to things, as opposed to the original Grassmann definitions, which are used in a lot of differential geometry and the original, Grassmann definitions. And so some of the newer modern geometric algebra literature unfortunately somehow diverges and uses the conventional expressions instead by default and implicitly in certain ways and expressions. And so it's important to understand this fundamental distinction that in some ways the expressions, the result of them, they'll overlap with each other and be the same in a lot of cases, and there'll just be some special cases where the results differ due to how the anti-automorphism application affects the definition. So the important thing which this table tries to emphasize when I created it was that some of the different literature out there will stick to some particular convention implicitly in their definitions, and which are different from the original Grassmann implicit conventions. And so I would like to be able to map that out and understand and differentiate that and be rigorous about the mathematical origins and meanings of these expressions and disambiguate the context of the language in these different contexts. Does this present any practical problems? Well, as if we just stick to the multiverse of the variance of interior products the way it is in this table here, it's not all too bad, because each of these expressions can be obtained from another one by applying some anti-automorphism to the input arguments of these expressions. And so it can all be recovered, and we can translate between these things, and it's not that difficult once you're aware of this, just to kind of keep track at the back of your head, you know, whether you need to apply some anti-automorphism when you're understanding different literature out there in terms of what variant of interior product is implicitly assumed in the definitions. Now, there is a particular reason why in the foundations of differential geometric algebra, as I have laid them out and constructed them so far, why I've chosen to use the original Grassmann convention and definitions in my work. It's because there are theorems and definitions which are found in some of the differential geometry literature, and especially in the Hodge and theorem things that have been written that are based on that. They will use some theorems and definitions which are compatible with the original Grassmann algebra, and some of the other geometric algebra literature, it has some slightly different implicit assumptions about how the anti-automorphisms are applied to the interior product contraction variance, then that is something to be aware of, and it could make some of the results incompatible by having a plus or minus sign end up in an expression being equal in such a way that it makes all of the mathematics inconsistent. So that is something you might have to worry about and be aware of, and that is one of the problems and issues I'm trying to address by having awareness of it with this table. But why is it important for me to have awareness about this issue with this table? Well, if we take it one step further and we consider that in some people's work they use a complement operation which is not exactly equal or the same as the original Grassmann complement operation or the Hodge complement as we discuss it here in this presentation and this foundations of differential geometric algebra. And so if you start changing that and you start changing, you know, the convention that you're using for left and right contraction, whether it's the Grassmann one or the conventional one, then that introduces potential errors and variabilities in expressions and results and theorems, that now it's no longer possible to say that some expression that person wrote in this when they made these other assumptions, that's at all compatible with the differential geometry literature or the original Grassmann algebra theorems that we're interested in. And so that's why in these foundations of differential geometric algebra, which I'm talking about here in this presentation, and which I've built and implemented in computational language with my Grassmann.jl package, and also into the Julia language and also the Wolfram language. The goal with all that is to have a foundation that's built on the correct, rigorous way of thinking in terms of the original Grassmann algebra, and having the awareness about different conventions and using formulas that satisfy the original theorems of the original Grassmann algebra. Because, you know, I've tested some of the other computer programs that other people have made, and when I check whether the Grassmann laws are satisfied with the complement operations and the regressive product and the exterior product, and trying out different ones of these theorems and expressions that should be satisfied, I find that it's not satisfied, and some of these computer programs that other people have written that claim to be about geometric algebra, they don't satisfy the Grassmann laws or some of the theorems that we've discussed here. And so that's why these foundations I'm building, that's why, you know, some people may have thought this is a boring presentation because it's just a bunch of math and some weird theorems and symbolic notation. But I'm actually trying to address some of the foundational questions and issues, and by building a foundation for differential geometric algebra in the way I have, then we can better understand what's going on in the geometric algebra literature. And if you do encounter some kind of weird discrepancies or errors or inconsistencies in the mathematics, it might be because you use some of these other people's literature where it somewhat diverged from the original Grassmann implicit understanding to a different implicit understanding. So as I've stated several times now, the goal here is to consider the foundations of differential geometric algebra. And the reason why we want to try to get this correct is because we want to be able to use some of the theorems from Grassmann algebra and use them with differential geometry and combine them with geometric algebra. And we don't want to have some kind of inconsistent, issues, because when you have an inconsistency, that can lead to just garbage mathematics. Like you might just have to throw some of that in the garbage if it's inconsistent. But just because there might be some issues like that, it doesn't necessarily they are, but there could be some that that I've encountered, for example, when I check some other computer programs. But when you're reading some of the literature, what you can do is you can try to get the gist of what it is the author is trying to get at, because there is something that they're trying to say, and recast it in terms of the foundations of differential geometric algebra, as I've been talking about here. Because that's what I do, at least for myself, is I try to recast the information that I'm receiving about from different sources about the mathematics of differential geometry and geometric algebra, and I try to make sense of it in terms of the theorems and definitions and foundations of differential geometric algebra as I've laid them out here. That's why I'm doing all this, and I decided I'll record this presentation so that other people can have some thoughts about this as well. Consider the situation where someone is selling a cheat sheet that has all this kind of information about formulas and tables of geometric algebra expressions, and suppose this is based on some computer program and some understanding someone has built up based around using some kind of complement definition that isn't quite equal to the original Grassmann or Hodge complement, or they've made some other choice about the convention in the variance of the interior product. It could be then that these tables and cheat sheets that you purchase, that they're going to be inconsistent with some sort of differential geometry literature that assumes that you have some kind of consistent theorems that satisfy the original Grassmann algebra theorems and axioms. So that's why this is something I like to investigate and think about and be aware about in my own research, at least. And unfortunately, there's going to be some people in teaching this who are going to want to create teaching material, but they're not nuanced enough with their definitions and foundations and implementation of what they're doing and talking about, that they don't satisfy the original Grassmann algebra theorems and axioms anymore. And so that's something that can happen with the ongoing development in history. As people try to spread more information, there's going to be some people who try to teach this material, but they weren't rigorous enough in their definitions. And there have been some people who I brought to their attention some details about the variance of the interior products and how the Hodge complement should be defined, and testing out certain expressions that should be satisfied due to the theorems based on the original Grassmann algebra. And they don't satisfy them, and I show the example, and they just don't want to be that rigorous about it when I confront them about it. And they just want to keep doing it their way because they think it's some kind of choice that you can make that makes sense for them from their perspective for whatever reason. Unfortunately, the issue is that if there is some kind of inconsistency that gets introduced with some of the other literature that makes assumptions based on the original Grassmann algebra, which a lot of the differential geometry literature is based on that. For example, the Hodge and theorem literature and the writings based on that. They're going to require a nuanced understanding of some of the definitions, and you have to be rigorous. And unfortunately, some of the people teaching this material, selling you cheat sheets and so on, those are not nuanced enough to really take into account all these things. And that's why when putting together the foundations of differential geometric algebra, I'm trying to address some of these things, and that's what this presentation is focused about. There's other presentations you can go to get more of an intuition about certain geometrical insights and things like that. Here, I'm mainly talking about the foundations of differential geometric algebra and what to be aware of. Computational language that's consistent, has the right kind of mathematical properties and theorems that's satisfied. We've now reached a point in the presentation where we can gradually stop climbing uphill, and we can reach a sort of plateau at the Grassmann-Leibniz mixed tensor algebra kind of review / overview, where we kind of have now covered enough of the foundations that we can talk at a more higher level about differential geometric algebra in the way that we'd like to see. So, two of the particularly interesting operations that we're going to get interested in are the so-called boundary operation and the exterior differential. And what's interesting about the boundary operation is that it satisfies what's called the Poincaré lemma. And that means basically if you compose the boundary operation with itself, that equals 0. This is just a fundamental property that you can check based on the properties of exterior algebra and the regressive products and the complements and so on. But how is this actually defined? Well, the boundary operation is basically we start to introduce the differential operation nabla, which is a sum of differential operators multiplied by the vector basis. And that's a mixed tensor now. We're now no longer just talking about the vector basis. We're talking about a mixed basis with differential operators and vectors combined. And that's why we have in differential geometric algebra in our foundations so far, we have considered both kind of tensors as part of our tensor algebra and part of the operations in our algebra. We can deal with both the vectors and the differential operators. And now we take the epsilon, for example, and take the regressive product with the complement of this nabla, basically. And that defines the boundary operation, which when composed with itself is equal to 0. And there's a similar thing that's called the exterior differential, and that's D. And that's formed by basically taking the nabla operator and wedging it, or taking the exterior product with the form omega. And that is similar to the curl and the cross product if you also apply the complement operation additionally in composition with the external differential D. So the more abstracted notation of the external differential and the boundary operator, they somewhat hide the fact that what we're doing is we're combining differential operators with the exterior product and with the regressive product, both by applying the Hodge complement to the expressions. And if we more explicitly write it out, then we can see what the definition is saying. But it's quite nice to have this compact notation offered up by the boundary operator and the exterior differential. It should also now be trivial for you to check that D applied twice, or DD, should also equal to 0 in a similar Poincaré lemma fashion as the boundary operator. And that's trivial to understand if you recall from the beginning of our presentation the property of linear dependence. It's a simple application of that property to see that D applied twice is also equal to 0. Now we'll get to one of the most important theorems of differential geometric algebra, which is the so-called Clifford-Dirac-Hodge Laplacian decomposition. So what we have is we have this thing that's in the literature called the Dirac operator. But if we study it carefully and understand what it is at its core, and we study the differential geometric algebra foundations, then we can understand that the Dirac operator is nothing but the square root of the Laplacian, which, you know, is a very great mystery if you do not know differential geometric algebra. But if you do know differential geometric algebra, it's not such a great mystery after all, because we can actually understand quite concretely what it is. And it's just the product of nabla and omega. And that's just the geometric product. And in particular, in this theorem, it's not just the geometric product. We have the decomposition of it into the sum of the boundary operator and the exterior differential. So it turns out that taking the sum of the boundary operator and the exterior differential is equal to this geometric product, which is a Dirac operator, which is the square root of the Laplacian, so to speak. But now, once you're aware of this Dirac operator, you can also check that the product that's in the theorem here is actually not commutative. And so if you swap nabla and omega, these are not equal to each other, the products. And however, with the Laplacian, that wasn't the case. those were equal to each other. It didn't matter whether you applied the Laplacian before or after, and that's because the Laplacian is a scalar quantity, whereas the Dirac operator is not. But we can observe that the composition of the operators can be done in several different ways and understood in different kind of expressional forms. Another theorem which is particularly interesting is the integration by parts theorem that can be fully generalized in terms of the Grassmann-Leibniz mixed tensor algebra. So in this situation, we let nabla be part of the Leibnizian vector field operator, and then we again use D and the boundary operator, and these turn out to be Hilbert adjoint Hodge theorem operators, which as a result satisfy these properties, and that's what this theorem says basically. So there's actually two parts to this theorem. I've kind of taken two parts to it and combined it into one. And there's this integral theorem with the integral over m of d omega times the wedge product of the complement of eta, and then plus the integral over m of omega wedge the complement of the boundary of eta, and that equals to 0. And another similar expression, it's not exactly the same expression, but it's a similar type of expression, meaning with a similar foundation, and that's when you basically take the inner product of d omega and eta and omega and the boundary of eta, and we can equate these two expressions to each other as a scalar product expression. And this is a particularly interesting theorem to just think about, and because it's a quite general statement. And this is also part of the reason why we set up all these foundations of differential geometric algebra, because we want to be able to reach a stage where we can talk about theorems like this, and we can be fairly certain about the foundations that we're satisfying the original Grassmann definitions and theorems and axioms that make the theorems that we want compatible and consistent with each other. Let's take a look at specific examples of the exterior differential and the boundary Poincaré duality by taking a look at the vorticity curl of a vector field. So that was by using the complement of D and applying it to dx1, dx2, and dx3. And if we apply this operator, we basically get the vorticity, the curl of the vector field, and that's what the result of that expression is right there. And so we're just going to explicitly take a look at the result of that just to gain some intuition. And in a similar way, we can take the boundary of a 3-simplex, which is these faces. Like if we take the boundary of v1, 2, 3, 4, that equals this sum, this particular result, which has a bunch of 2 simplices in it as a sum, and differential operators and orientations and so on. And similar to the vorticity curl of the vector field, this is a particular operation in differential geometric algebra, which combines the geometric algebra operations with the Grassmann exterior algebra basis and the differential operator TensorAlgebra basis. Another interesting form of expression that we can start playing around with is when we combine the boundary operator with the grade projection operator and make expressions that way. For example, if the rank of the grade P boundary incidence operator is written in this expression by taking the minimum of these two dimensions of these operators by doing this calculation and just calculating the dimension of the vector space that results from the calculation. And if some of the coefficients are 0, that changes the rank of the result, and that's where this kind of information leads to invariant topological information that can be computed using the rank of homology groups for Euler characteristics, which is written chi. And this is the sum of a bunch of these numbers, which are called Betti numbers or Betti coefficients. And we can explicitly compute and play around with some of these in a similar fashion as the rank of the grade B boundary incidence operator. We apply that over and over again several times in such a way that's related to the Hodge decomposition. And by taking the sum of the series of coefficients, we get the Euler characteristic. So this is something that's might be interesting to a bunch of topologists who are interested in the homology and cohomology groups and invariant topological information in differential geometric algebra. Let's take a moment to think about how we simplify Maxwell's equations into a single wave equation. So we can just start by taking the definition of a Faraday bivector dA with dDA equal to 0. So as we know, if we have something like dA, dDA has to equal to 0 just from linear dependence, just because of what we know about exterior algebra and the Grassmann foundations. And we define the Faraday bivector dA as E times Vt plus the complement of B times Vt, where E is the electric field and B is a magnetic field and A is the vector potential. And that's just a definition of the Faraday bivector. Now, we want to think about Maxwell's equations, and they should be transformed into a single wave equation, right? That's one of the goals of, or one of the things advertised about geometric algebra or differential geometric algebra. And since we already know dDA is equal to 0 just by definition, by the definitions of what we already have talked about in the foundations of differential geometric algebra, Gauss's law and Faraday's law are already a given just from the definition of the Faraday bivector. So we don't need to do any additional work when we recognize that Gauss's law and Faraday's law correspond to dDA is equal to 0. But we do need some additional thinking when it comes to star D star dA is equal to J. And this is what we really mean when we talk about simplifying Maxwell's equation to a single equation, because what we end up creating or talking about is the Laplacian of A equal to J, which is the Maxwell's equations written as a wave equation in terms of geometric algebra. And when we really think about this, is star D star dA, or the geometric product of nabla times dA, as I show in the expressions. And these two correspond to Gauss's law and Ampere's law. these star d star dA equal to j. And as a result, that's how we get Maxwell's equations rewritten as a single equation, because we know that dDA is equal to 0, so we don't need to define that equation or really talk about it, because it's kind of by definition and by the properties of everything that's going on in differential geometric algebra. But the equation that we do need to worry about is star d star dA equal to j, and that's simplifying Maxwell's equation into a single equation. Here I'd like to share one of my favorite proofs in differential geometric algebra, which is the Dirac operator decomposition reveals rotoreflections. And this can be broken down into two separate parts, and the first part is the one that's particularly interesting for me. And this is the theorem where the first grade sandwich product is a reflection. And so when we have a reflection by a hyperplane, such as the complement of nabla, that has the isometry omega O slash nabla, which is, this symbol combination is defined as negative nabla backslash omega times nabla. And what the backslash just means is that there's a division going on, but it's on the left side of the expression, so we're inverting nabla and then doing the geometric product to multiply them together. But since it's on the left side of the expression, the division has to be a backslash, and that's why it's written like that. And in order to, simplify all that notation to avoid having to remember all that, that's why omega O slash nabla is supposed to be like a simpler notation, which means we have omega and we have nabla, and we do an operation called O slash on them, and that's supposed to be a reflection basically. And that's a theorem, that it's a reflection and that this is isometry. And the way I can prove this is basically we let nabla be grade 1 element, then omega equals nabla, divided by nabla times omega. That's just kind of multiplying by 1. But we've introduced more symbols, and we can apply the associative property and reparenthesize the expression. And when we start doing things like that, we end up with a different expression, and we can now have nabla backslash d omega plus boundary of omega. And if you recall from our previous theorems, that's an application of the Dirac operator and the decomposition of that, which was d omega plus boundary omega, which is also a geometric product of nabla times omega. And due to the way we have now restructured the way we write omega by introducing this expression, which was initially just multiplying by 1, we have now expanded it out and written it in a completely different way. And what's particularly interesting about this new construction is that nabla is parallel to the boundary of omega, and nabla is also perpendicular to d omega. And if we understand that, we can do the reflection, and we can understand that we reflect by flipping the component that's perpendicular. And so we reflect across the hyperplane, which is the complement of nabla. So let's do that. So we want to prove this by doing the reflection and then getting the expression back that we want to prove, basically. So what we want to prove is that this expression up there is a reflection by hyperplane from the element omega using this hyperplane that's the complement of nabla, basically. So we take the expression of omega that we had and we apply the reflection, and we now have a different expression, which is nabla backslash d omega minus boundary of omega. And now we multiply this expression by 1 again. We do the same trick all over again that we just did before. And we rearrange things with the associative property, and by rearranging things a bit with knowledge of the geometric product. And by applying knowledge of the Dirac operator, once again, d omega plus boundary omega, we can replace that with the product of omega and a nabla. And since that right there was a nabla squared, which we got from rearranging the product before, we now end up with minus nabla backslash omega times nabla. And that's the expression for reflection by hyperplane. So we can kind of have an algebraic proof that the reflection by hyperplane complement of nabla has this isometry omega o slash nabla, where omega o slash nabla is the minus nabla backslash omega times nabla. Why does this matter, and why go through this weird proof that shows that reflection by a hyperplane can be expressed in terms of this formula? Well, this is the same formula which generalizes, and using that formula we can express the Cartan-Dieudonné rotoreflection decomposition, which is a theorem which has been, discussed in the literature of geometric algebra and in other various places before. So if we have this foundation of differential geometric algebra, which we've been talking about, and we take this theorem which I just showed you and proved for the reflection by a hyperplane, which results in the grade 1 sandwich product formula, that can be composed in several layers so that every isometry from the vector space V to itself is the composite of at most k reflections. And so that's what the Cartan-Dieudonné reflection theorem says. And the way we can express it in terms of a formula is using this O slash notation, where omega O slash nabla 1 and then composed with O slash nabla 2 and so on up to nabla k is equal to omega O slash of the geometric product of nabla 1 times nabla 2 up to nabla k. And so what this helps us understand is that we can express the decomposition of every isometry into a composite of at most k reflections by observing the formula for reflection and nesting it several times. And that's why the theorem which I proved above was particularly interesting. And I don't think I've seen a proof of this theorem before. This is my original kind of insight about how you can prove that a reflection by a hyperplane has a isometry, and this uses the Clifford-Dirac product decomposition d omega plus boundary omega as kind of a application. And that's why I thought this was an interesting theorem to take a look at, because when you apply that repeatedly, that's the Cartan-Dieudonné rotoreflection decomposition theorem, when you express it in that way. And you can think about that, check that for yourself. That's why I go over these mathematical details here, is because it's not just computational language that has to be implemented, but it's mathematical theorems and definitions and axioms that have to be satisfied, that in order to be rigorous about this, in order to be able to seamlessly use this in an engineering environment to calculate with mathematical physics and use differential geometric algebra all in a neat and unifying way, and to have it be convenient, it's necessary to look at the mathematical foundations and the theorems and to think about the proofs a little bit. And that's why I've had this long presentation and took some time to revisit some of these things. What that leads to is the design of the computational language that I ended up with, and I put into my code repository on GitHub, Grassmann.jl, and I've now written a paper about it and included a bunch of the theorems, and some of the information discussed in this presentation is all included in the paper about the foundations of differential geometric algebra, which I conceptually developed alongside programming and developing and researching and designing the computational language for Grassmann.jl. And while I was doing that, I was gathering my thoughts about the foundations of differential geometric algebra, and that's how this presentation came about, and that's how I put all this information together, by writing a paper about it. And so what does all of this mean for the future of mathematics and engineering? Well, of course, the goal with this type of designing of computational language is to improve the efficiency of multidisciplinary research using differential geometric algebra by relying on universal mathematical principles. And that's why I based this presentation on the foundations of differential geometric algebra, and why I went over some theorems and proofs, and why I took a look at some of the definitions, and why I use all this language to talk about these things is because in this particular presentation, I'm not necessarily trying to say that this is how this should all be taught to people, and how the teaching should happen and how the learning should happen. But it is part of how the foundations should be constructed, where from what to derive, the notation and the understanding that we're going to build. Because we need some kind of starting point, some kind of complete understanding. There needs to be a foundational understanding behind all of the other derived understanding, so that it all makes sense and is consistent and has a greater meaning behind it. And that's why getting the foundations right is important, and that's why this presentation is trying to organize the foundational principles behind some of these things about the foundations of differential geometric algebra. What are the present challenges? Well, it's not yet standardized or taught in schools and universities, and not yet used for industrial science and engineering unification. And so some of the challenges I've mentioned also, that some of the notation, some of the implicit assumptions made about the interior product, for example, and the complement operation, and how the Grassmann laws should be satisfied. Some of those nuances may not have been rigorously thought about by some of the people writing, but I rigorously thought about it when I was programming the computational language design and these foundations I'm talking about here. And it's based on the original Grassmann complement operation and satisfying the original Grassmann algebra laws. and that helps unify things with the differential geometry literature, such as the Hodge and the theorem writings that have been written later on, and things that are based on that. And there's been some modern geometric algebra writings which took a slightly different direction and took implicit assumptions about how inner products work, which somewhat diverges from the original Grassmann, and because of that there might be some inconsistencies. And I posit that the original Grassmann way is of course the correct way of doing it, because that's also how the differential geometry bases some of its assumptions and its theorems. And getting these foundations correct and thinking about correctly matters, because all the other things that get derived from it downstream have to be consistent as well. So these are some of the present challenges about it not yet being standardized or taught in universities and schools yet, because some of the textbooks and things, they're not necessarily based on this full understanding and may not be consistent with it. And that's why Grassmann.jl, the software, enables ascending future steps. So that's why I created a computational language implementation, and I designed it based on these foundations so that it can be rigorous, and so that it can be used to help gain a understanding about how the consistent mathematics should be understood, so that there's some kind of access to getting a consistent and correct answer that's consistent with the original Grassmann algebra theorems. And so it's called Grassmann.jl for a reason, because some of the other implementations out there, I haven't tried them all out, but some of the ones I have tried out, they don't necessarily satisfy the original Grassmann laws. But the emphasis in my program is to try to satisfy the original Grassmann laws, and to help from that derive the correct understanding, making sense of things in the world. And that's why I created this Julia package, Grassmann.jl, which is available on GitHub. And these fundamental mathematical principles, they're universal, so I could be implementing them in a variety of programming languages. And before I even implemented it in any language, I spent a long time thinking about it and constructing it in my mind. And these things have to be understood before they can be transmitted further, and there has to be a little bit of rigor behind it. And that's why we have taken a look at some of the theorems and so on, and trying to address some of the challenges with miscommunication about how the original Grassmann algebra theorems may not be satisfied by some people's work because they didn't rigorously think about the foundations yet or something. I don't exactly know, but I'm just trying to provide my perspective of how the foundations should be constructed for foundations of differential geometric algebra, and Grassmann.jl is a particular implementation of that in computational language, which manifests these abstract concepts I talked about in computational language. And using that, I verify my thoughts about it. I can use it as a tool to teach myself and to teach other people and to show them why I'm a proponent of the foundations of differential geometric algebra here, so that we can have further discussions that build upon it further, and further computational language designs, and further insights that keep building on the science and the mathematics. When I set out to work on this, the tools I desired based on these foundations didn't exist. So I went ahead and created the kind of foundations I envisioned. Please help sponsor and fund this research and development project. There is a need for funding of mathematical research project outside of academia.